Okay, let's start our afternoon session. The first speaker is Sergei Lando, weight system related to the algebra. Please.
Thank you, Sasha. First of all, let me show a list of papers related to the subject I'm going to talk about right now. This is not a complete list, and several people are involved in this research, mainly my students, Jockey Young, who is present here now, who is now a member of BIMSA, Polina Zakorka, who is also here, Polina Filipova, now Polina Zinova, and Nadia Kadaneva, as well as Maxim Kazaryan, who is an ideological, probably, leader of the group. And what this is all about. This is related to study of knot invariants in the framework of Vassiliev's theory of finite type knot invariants. In Vassiliev's theory, any knot invariant taking values in a commutative ring can be extended to singular knots. We start with smooth knots in the 3 space, and according to Vassiliev's scaling relation, we extend the invariant to singular knots, and a knot invariant is said to be of order at most n if its extension to singular knots with more than n double points vanishes completely. To such an invariant, one can associate a function on chord diagrams. Chord diagrams are very simple combinatorial object consisting of the circle, which is the Wilson loop from Nikita's talk. The circle endowed with several chords, and chords in our case, having pairwise distinct ends. And this function, this extension, must satisfy the following Vassiliev's 4-term relations, which look like follows. We have a chord diagram. We have 2 chords with neighboring ends, and starting with these 2 chords, we construct 3 more chord diagrams, such that they can have additional set of chords, which is the same for all chords having ends on dot arcs of the diagram, while the distinguished 2 chords acquire these 4 possible positions. To each finite type knot invariant, one associates a function on chord diagrams, and the famous Kontsevich theorem states that the converse essentially is also true, so that each weight system taking values in an algebra over a field of characteristic 0 arises from some finite type knot invariant. So that there is more or less one-to-one correspondence between weight systems and finite type knot invariants. It is, of course, interesting to construct weight systems, to construct in some way functions on chord diagrams that satisfy 4-term relations. And there are 2 main sources of such constructions. One source is graph invariance. I'll explain how it works, but I will speak mostly on the other class of constructions, namely constructing weight systems from Lie algebras. The main difference between these two constructions is that those weight systems that come from not from graph invariants are usually can be easily computed, but they are not powerful, while those coming from Lie algebras are extremely powerful, but it is very hard to compute them generally. How the construction from Lie algebras proceeds? We start with a finite dimensional Lie algebra G, endowed with a non-degenerate invariant scalar product. The invariance meaning that for any triple of vectors x, y, and z, the scalar product of the commutator of x and y with z is the same as the scalar product of x with the commutator of y and z. And then we proceed as follows. Pick an arbitrary orthonormal basis x1, xd in the Lie algebra, then cut the circle at some point, which can be arbitrary, and develop the outer circle into the straight line. After this, what we obtain is an arc diagram. Chords become the arcs, and we put one and the same element of the basis at both ends of the arc. As a result, what we obtain is a word, a product of the elements of the basis, which is an element of the universal enveloping algebra. And then we sum these elements over all possible ways to mark the arcs of the diagram with the elements of the basis. An easy theorem due to Dror-Barnatan and in a different form to Maxim Kontsevich states that first, the result of such summation is independent on the choice of both the basis, the orthonormal basis we have chosen, and the cut point, so that we obtain a well-defined element of the universal enveloping algebra of G, which in fact belongs to the center of this universal enveloping algebra, and this mapping taking a chord diagram to the center of the universal enveloping algebra satisfies the four-term relations, so that what we obtain is indeed a weight system. However, whatever easy is the definition, it is a very hard task to compute the result, because we are obliged to make computations in a non-commutative algebra, in a highly non-commutative algebra, which is the universal enveloping algebra of the Lie algebra. And in spite of the fact that the result belongs to the center of this universal enveloping algebra, which is a commutative algebra, all the intermediate computations are to be made in a non-commutative situation, which makes them extremely complicated. With a single exception, for the simplest Lie algebra SL2, there is a recurrence relation due to Sergei Chmutov and Alexander Vashchenko, which allows one to compute the values of the SL2 weight system directly, not using it, not making intermediate computations in the universal enveloping algebra. That is how this recurrence relation looks like, how it works. It happens that in any sufficiently complicated chord diagram, there is a triple of chords either in the position shown in the first line or in the position shown here. Once again, on this solid arc, there are no intermediate arc chord ends between the ends of these two chords as well, here and here as well. And in this case, one can replace a chord diagram, but by 5 more simple chord diagrams, the first 3 of which have fewer intersections of the chords, while the last 2 have fewer chords. So that this is indeed a recursion relation which allows one to replace a chord diagram with simpler chord diagrams. And we may proceed recursively computing the results of this, computing the value of this SL2 weight system. However, even this algorithm is rather complicated because we replace a chord diagram by 5 other diagrams at each step, so that we have an exponentially complicated algorithm which does not allow us to proceed much further. And until recently, the explicit values of the SL2 weight system have been known only for fairly simple chord diagrams and families of chord diagrams. In 2007, Sergei Chmutov and me, we proved that the value of the SL2 weight system on a chord diagram depends on the intersection graph of the chord diagram only, not on the diagram itself. The intersection graph is a simple graph whose vertices are in one-to-one correspondence with the chords in the diagram, and 2 vertices are connected by an edge if and only if the corresponding chords intersect one another, so that one may speak about the value of the SL2 weight system on graphs that are intersection graphs of the chord diagrams rather than on the chord diagrams itself. And I will proceed like that. In order to explain the following theorem due to Polina Zakorka, I have to address another invariant of graphs, which is in fact a weight system. If you consider it as the invariant of intersection graphs of chord diagrams, and this invariant is a very well-known chromatic polynomial of a graph. The chromatic polynomial counts the number of proper colorings of the vertices of a graph into a given number zero of colors. And it is easy to see that if our graph is the complete graph on n vertices, the complete graph on n vertices, which is a graph for which any 2 vertices are connected by an edge, then the corresponding chromatic polynomial looks like c times c minus 1 times c up to c minus n plus 1, which is the following factorial of c, of the number of colors. We are able to color the first vertex in arbitrary C colors, then the second vertex. For the second vertex, we can choose C minus 1 colors that are not coinciding with the first one, and so on and so forth. And there is a very nice formula for the generating function for these following factorials, for the generating function for chromatic polynomials for the complete graphs, which represents them as the Jacobi continued fraction. 1 over 1 minus ct plus ct squared over 1 minus c minus 2t plus 2 times c minus 2t squared, and so on. So that the case rho in this continued fraction looks like 1 minus c minus 2 times k minus 1t plus kc minus k times k minus 1 over 2t squared. It happens that for the values of the SL2 weight system on the complete graphs, on the chord diagrams in which all the chords intersect one another, a similar continued fraction for the generating function takes place. You see, this generating function also starts with the following factorials, but already the fourth term is different. It is c times c cubed minus 6 c squared plus 13c minus 7. And the formula for continued fraction, also very similar, is different. Instead of 2k minus 1 in the linear term, we obtain k times k minus 1 here. A linear polynomial is replaced by the square polynomial, by the quadratic polynomial in k. And here, instead kc minus k times k minus 1 over 2 t squared, we have k squared c minus k squared times k squared minus 1 over 4. This conjecture, I came to this conjecture around 2014, but was totally unable to prove it until Paulina found a nice way to argue. And in addition to proving this formula, she developed several instruments for treating SL2 weight system on so-called shares, which allowed Maxim Kazaryan and Polina Zinova to compute explicitly generating functions for the values of the SL2 weight system on complete bipartite graphs, which can be written in the form of a recurrence formula for corresponding generating functions, where the coefficient SIM here also are given explicitly, so that during the last couple of years we have got numerous highly non-trivial families of chord diagrams for which we know the values of the SL2 weight system explicitly. And at the moment, the last result in this direction is the SL2 duality, which generalizes the results for the complete bipartite graphs in the following form. A complete bipartite graph can be considered as a join of two graphs, of two discrete graphs on M and N vertices respectively, and instead of these graphs, we can consider families of joins G n for an arbitrary graph G and a discrete graph on n vertices. Zakorka and Zinova and Kazaryan proved that the generating function for the values of SL2 weight system on these families of joins have a similar form. They are linear combinations of rational functions whose denominators are 1 minus c minus m times m plus 1 over 2 times t with the polynomials with the, whose numerators are polynomials in C for some sequence of polynomials depending on the number, depending on the given graph G. And Polina Zakorka and Polina Zinova proved a duality formula for these polynomials. It happens that if we know these polynomials PMG of C for some graph G, then we also know them for the dual graph. The dual graph, the complement graph of G, G bar, is the result of, we take a graph G, we preserve the set of its vertices, and we switch all the edges in the graph. The set of edges in G bar is complementary to the set of edges of G. And then the polynomials PMG for G bar remain the same, but half of them changes the sign, so that this is indeed a duality. The paper will appear on the archive the day after tomorrow, I hope. Will finally appear. But what can be said about more complicated Lie algebras, about more general Lie algebras? SL2 is just a single example which corresponds to a very powerful and influential not polynomial, which is Jones, which is colored Jones polynomial, but there are much more powerful Lie algebras. And for the series GLN, Maxim Kazaryan suggested an idea which proved to be extremely fruitful. The idea is to construct a recurrence by extending the weight system from chord diagrams to permutations of more general form. In fact, Maxim Karev, who participated the previous part of the conference, explained to me that this construction of extending weight systems to permutations was contained implicitly in his paper with Sergei Duzhin. I do not remember, maybe around 2007, but there was no recurrence and no idea how any reasonable computations could be done. In order to explain this construction, I will modify slightly the construction of the weight system from Lie algebra, and instead of an orthonormal basis, I'll consider an arbitrary basis in the Lie algebra, and in this case, what we write on the left end of the corresponding arc, we write an element of the basis, while on the right end of the same arc, we write the dual element of the basis, the dual with respect to the chosen non-degenerate scalar form, and it happens that the result will be, in fact, the very same element of the Lie algebra, whatever basis we have chosen. In this construction, it is easy to see how the GLN weight system can be extended to permutations. If you take for the basis in GLN, we choose the standard basis of matrix units, EIJ, so that EIJ corresponds to the n times n matrix having 1 on the intersection of the ith row and j's column, and all whose other elements are 0. And the symmetric matrix EJI is the dual to the matrix EIJ with respect to the standard to the standard scalar product given by the trace of the product of two matrices. And now the key construction. If you take an arbitrary permutation of arbitrary number of elements, m, then we are able to associate to this permutation an element in the universal enveloping algebra of GLN, which is the sum of the products of matrix elements. The products are understood as the products in the universal enveloping algebra rather than matrix products. We take I1, I sigma of 1, I2, I sigma of 2, and so on and so forth. And then we sum these products of matrix units over all possible ways to number the permitted elements with indices from 1 to n. Now, an easy statement, maybe not that easy, but it is also true that the result of applying this mapping to an arbitrary permutation sigma provides us with the element of the center of the universal enveloping algebra of GLN. And in order to explain the recursion, I will need the notion of a simple notion of a graph of a permutation. We simply, in order to describe a permutation, we just put all the permuted elements along the straight line, and in blue, we show the arrows showing where each element is taken by the permutation. 1 is taken to n plus 1, n plus 1 is taken to 1 in this example. This is an example of a permutation in which all the cycles are of length 2, so that this is an involution without fixed points. And in this way, chord diagrams can be described. Chord diagrams or arc diagrams, they describe, they can be considered as permutations which are involutions without fixed points. And it is easy to see that for the Lie algebra GLN, this construction of weight system GLN on permutations exactly coincides with the construction, with the original construction of the weight system on chord diagrams, so that this is indeed an extension. This is indeed an extension of the GLN weight system to arbitrary permutations, not necessarily chord diagrams. For the standard cycle, one goes to 2, 2 goes to 3, and so on. M goes back to 1. The value of the corresponding weight system, GLN, we define that this is the M-Casimir element of the center of the universal enveloping algebra. And the well-known classical theorem states that for a given n, the center of the universal enveloping algebra GLN is naturally identified with the ring of polynomials in the variable C1 up to Cn. So that our weight system on permutations takes values in the ring, in the polynomial ring of polynomials in n variables. And now we are coming to the recurrence. In this recurrence, we represent any permutation as by means of its directed graph, the directed graph of the permutation. And if you take two arbitrary neighboring permuted elements, L and L plus 1, then we are able to exchange them, to exchange these elements, to switch them for the price of the difference of two permutations of the values of the GLN weight system on two permutations of smaller number of elements. Here on the left we have each of the two permutations permutes m elements, one, while on the right each of the two permutations permute m minus 1 elements. And this is indeed a recurrence relation which allows one to replace a single permutation of n elements with three permutations, with three simpler permutations. And this is the first, using it we are able to to construct effective algorithm of computing the value of the GLN weight system on permutations. Here is a special case of this construction when our permutation takes an element k plus 1 to the element k, then we are able to undo this intersection, and here will appear the element C1, and here will appear n, which is the rank of the Lie algebra GLN. As an example of this computation, we are able to compute the value of the GLN weight system on the cycle of length 3, which is inverse to the standard one. And here the cycle is 1, 3, 2. By replacing the elements 2 and 3, we get the cycle 1, 2, 3. And what's happened on the right, we already know, so that the value of the GLN weight system on the inverse cycle is C3 plus C1 squared minus n times C2. Well, an immediate and very important corollary of this construction, of this recurrence relation, is the following one. It happens that we are able to glue all the GL and weight systems together in a single universal GL weight system, which takes place in the ring of polynomials in infinitely many variables, the first of which is n, which is nothing but C0, and all the other Casimirs of all possible with all possible indices. And if you have this universal enveloping, universal GL weight system, then we are able to specialize it for any given value of n. In order to do that, we preserve C1, C2, Cn, substitute n equal to the specific number, and use a standard expression, a standard way to express the element Cn plus 1, Cn plus 2, and so on in terms of the first n Casimirs. Now, this was exactly, this is the argument, and the way of reasoning is very similar to what Andrei Kontsevich explained for going to infinity in the way in characteristic classes. So now we have a very explicit construction for GL weight, for the universal GL weight system for chord diagrams and more generally for permutations. And we are able, we have an algorithm to compute it, but and then what we get, for example, for the chord diagram consisting of 5 intersecting chords, we obtain a huge polynomial in variables n, C1, C2, and so on. And it is very interesting to understand what kind of information is encoded in this polynomial. The polynomial is huge, and from the first glance, it is not clear how we can use it and obtain, how we can use it and obtain some reasonable information. While you were leaving, I was mentioning you. How can I? What kind of information does this polynomial contain? One way to make this question more precise is to ask which graph invariants can be extracted from these polynomials. And there is at the moment we have already a number of rather non-trivial statements. It is easy to show, for example, that there is no substitution of the values n and the values of Casimirs that makes this polynomial into the chromatic polynomial of the intersection graph. However, it happens that if we make the substitution ck equal to x to the power nk minus 1 for all possible values of k, then we obtain a polynomial in two variables, which are now n and x. And if we take the leading term in n of this polynomial, then this leading term on a chord diagram becomes, it is a polynomial in X, which is exactly the chromatic polynomial of the corresponding intersection graph, which is a rather unexpected situation. Moreover, if we replace our chord diagram with an arbitrary positive permutation, then the assertion of the theorem remains true. By a positive permutation, I mean a permutation in which all the elements in each cycle go in one direction. But the last one, from the last one, we return back forwards. And there is a number of other theorems related to this chromatic substitution. Other graph invariants, a number of other graph invariants also can be extracted from this polynomial. Here I mention only that there is a substitution which provides what is called interlaced polynomial of a graph. And this result is due to Nadia Kodaneva and myself. I'm not given the definition of the interlaced polynomial, but nowadays it is a rather interesting and well-investigated polynomial. What's interesting about that? So we have a substitution which provides for chord diagrams the interlaced polynomial of its intersection graphs. But the substitution is well defined for arbitrary permutations as well, so that we obtain some polynomial invariant of permutations. What can be done with this polynomial? What is the interlaced polynomial of permutations? What are its properties, and what is its meaning? In addition to weight systems constructed from Lie algebras, there is a similar construction for weight systems from Lie superalgebras endowed with non-degenerate invariant scalar product. And Jokiyan elaborated as well the extension of the corresponding weight system for the Lie superalgebra GLMN to permutations, and he has shown that this extended weight system can be extracted from the weight system for the Lie algebra GLN if you set n capital equal to the difference of m and n in the defining for the ranks of the weight system of the Lie superalgebra weight system. And for other classical series and of Lie algebras and Lie superalgebras, the result is also obtained by Maxim Kazaryan and Jokiyan, and I still hope that the paper will appear in the nearest future, although I hope for this for already half a year or so. What is the relationship of these pictures to what Igor Krechever has been done, and how these objects are related to his field of interest? During the last decades, one of the most close domain of research to Igor was the theory of real normalized differentials on algebraic curves. A meromorphic differential on a curve is real normalized, provided all its periods are real, so that the integral of this differential over any closed curve on the surface is real. And Igor hoped that real normalized differentials can be useful, and in a number of important examples, he has shown that they can be useful in understanding the geometry of moduli spaces of algebraic curves. For the case of real normalized differentials with a single pole of order 2, the relationship can be established as follows. If any such differential determines a line field on the curve x. This is the field of lines looking in the direction in which the integral of the one form omega increases. The imaginary part of the integral increases, the real part is preserved. This line field has several separatrices, such that if you cut our surface over the separatrices, then what is left is just a cell, and there is a natural mapping from this cell to the complex line, the image of which is a complex line cut along several half lines. These half lines are split into pairs, starting at one and the same level, so that in fact these half lines determine an arc diagram. We are able to, if we connect the corresponding lines with an arc, what we obtain is an arc diagram. And the space of meromorphic differentials is stratified according to this arc diagram. This arc diagrams number strata of the highest dimension in this stratification. The second Vassiliev move, which appears in the four-term relation I have shown in one of my first slides, the second Vassiliev move is exactly what happens with this strata as we cross the walls in this stratification. So that this stratification is very closely related to arc diagrams, but not only to arc diagrams, but also to more general permutations, since as the separatrices collide, we obtain strata of higher codimension in our stratification in the moduli space of meromorphic real normalized differentials. These strata of higher codimension are enumerated by permutations of more general form than chord or arc diagrams. Let me now discuss some. There is a huge number of problems. Each time we discover some new direction, new approach to old problems, a huge number of new problems emerges immediately. For example, this problem is an old one, and this problem is the one which initiated our study of SL2 weight system. As I have mentioned, the SL2 weight system depends on the intersection graph of a chord diagram rather than on the diagram itself. A natural question is whether the SL2 weight system can be extended to arbitrary graph, not necessarily those graphs that are intersection graphs of chord diagrams. And this extension should satisfy the four-term relation drawn on my T-shirt, so that it would be very interesting to know whether such an extension exists, and I hope that the results obtained in the form of explicit computations can help a lot to achieve this goal. A partial answer given by Fomichev and Karev, who, as I have mentioned, took part in the first part of this conference, says that this is possible for the value of the SL2 weight system at the C equal to 3/4. They use a different normalization. In the normalization I was spoken about, it is 3/4. But we don't know about other values of C, most of the values. The paper by Fomichev and Karev appeared on arXiv 3 days ago or so. Now, I've told you that the chromatic polynomial appears as the leading term of the universal GL weight system under the substitution Ck equal to x to the n to the power k minus 1. But there are other terms as well. For example, what about the second term of this asymptotics? What combinatorial meaning does it have, and what is how we can interpret this this term and the other terms as well? And what is the combinatorial meaning of the chromatic polynomial, of the chromatic substitution for arbitrary permutations, not necessarily chord diagrams? Interlaced polynomial also leads to similar questions. Now, chord diagrams can be treated as orientable maps, combinatorial maps with a single vertex, while permutations are orientable hypermaps with a single vertex. What about more complicated maps and hypermaps where we do have arbitrarily many vertices, not just one? And in the stratification of the space of meromorphic differentials, I have talked about chord diagrams, and permutations come not as combinatorial objects, but as metrized objects. Each arc here has a length, which is the integral of our differential form between the corresponding points. One can write down four-term relations for this continuous situation. What is this meaning? What is the meaning of these four-term relations, and how we can construct invariants, more general invariants in this continuous case? And there is a huge number of other problems and questions, but I have no time to discuss them right now. Let me stop here.
Thank you very much. Question, please.
I have a couple of questions. So first of all, maybe there are framed versions of all of that. I mean that we can have framed chord diagrams, and it seems logically that superly algebra stuff should be variable if we have 0 and 1.
Yeah, I totally agree with you.
And the second question is, maybe if we consider something which is not realizable by chord diagrams but by permutations, maybe it can be related to unitrivial and Feynman diagrams, which were impolitely called by Barnatan in his initial paper on the Vassiliev non-invariants.
In this case, I'm not quite sure, because these Chinese characters, how they were called by Barnatan, they are used to express chord diagrams. There are some linear combinations of chord diagrams. For permutations, this is not true. They cannot be expressed as chord diagrams.
Yes, but maybe if we consider such a Chinese diagram, maybe there is an intersection which is realized not by a chord diagram, but something like that.
Maybe.
Okay, thank you.
Thank you. More question? Thanks again.